for the talk. But the two terms that you need to remember here is confidential computing and promises and promises. And as you will see later in the talk, it's not a mistake why this word is repeated twice. Yeah, you'll understand this throughout the talk. So what I'm going to talk about today is maybe the evolution of one particular instance of or implementation of confidential computing environment. And in general, what is now called confidential computing has a very long history. It's not entirely illustrated here. It starts around the 70s when the first implementations of secure crypto coprocessors were created, and later on that evolved to further secure coprocessors that were, let's say, platform specific from IBM in 1999, and then followed by something called Trusted Platform Module, what was based on a open specification. So all of these had, of course, slightly different functionalities, or maybe even very different functionalities. But the central idea around them was to be able to compute certain cryptographic functions, generate keys, decrypt and encrypt data in a secure environment, so where there's a guaranteed security of the environment, and ideally they would be even tamper-proof, so that an adversary who has access to the platform cannot extract the keys. So they are very widespread. Even probably everyone, each of you has one in a pocket, and that's, for example, the crypto processor on the credit card that you have, or maybe on the other smart cards. But then later on, the paradigm started to change. We started moving into a more software-driven world and cloud-driven world. And it's not really convenient to go and plug in a hardware card into a platform in a data center, especially if the data center is located very far away or underwater or in some other conditions. And so platform vendors started to come out with new models of let's say, such secure environments that would be mostly driven by software with hardware support, and that would be more flexible and more scalable. So ARM created its own first version around 2005, but it was not very scalable in the sense that it simply divided the platform into two, let's say, worlds, a secure world and a normal world. And then the applications in the secure world could communicate through a certain interface with all the other applications running on the platform through a security monitor, but there wasn't any isolation among them. So if something went wrong, then the whole security was compromised. Then in 2013, Intel came up with this new paradigm that allowed to create multiple enclaves that replaced this rigid limitation of like one environment, one secure environment, and instead multiple secure environments could be created on the platform that was very cloud friendly, that was very forward-looking, and let's say when it was first published, it raised a lot of expectations, and today we're going to talk about this. So this story continues. The Trusted Platform Module, the chip approach, still is very widely used. There was a second version of it in 2014, and it keeps being updated. On the other hand, other vendors chose to add additional isolation features, so memory protection features for virtual machines. So that is a different branch that is also kind of cloud compatible or cloud friendly, let's say, approach to confidential computing. Now we're going to talk about software guard extension, so SGX that I mentioned before. It was introduced in 2013, and it's a set of instruction set of architecture extensions that allows to set up these enclaves that allow isolated execution on the platform, which means that the execution is isolated from the rest of the operating system. It has its own environment, its own part of the memory. And different from the hardware approach, it allows to run arbitrary code. So you can run all sorts of applications. They might need to be adapted a bit, but you can run all sorts of applications in these enclaves. And this made a huge difference compared to the earlier approaches. And most importantly, in line with our previous work on trusted computing and confidential computing, it maintains support for attestation, and that is the ability of these enclaves that are created, or these secure environments that are created, to prove to some remote entity, perhaps the end user, that they were set up correctly, that they're running on a real platform, that they are running the code that is intended to run, and nothing else, for example, was added, and there's no modification of the code. So that's very promising. And most importantly, if you do security, what you care about is the adversary model, because we know that we cannot have absolute security, but what we have is a set of constraints, and that's the adversary model. So if you don't do security, then let me introduce you. You always have a couple of friends. These are Alice and Bob that might want to communicate, and then you have Eve, who is the adversary, the evil Eve, and who wants to obtain some sort of information. And what defines an adversary model are the capabilities of Eve, what can Eve do, and the conditions in which Alice and Bob communicate. And here, the vendor, the authors of SGX, software guard extensions, they really raised the expectations really high. So what was published initially is that only the CPU is trusted, and they assumed that, of course, users would be running trusted code in the enclave. So like no malicious, no evil code in the enclaves. Of course, they want to trust on the good. They want to run on the good, useful code in the enclaves, and everything else is untrusted. So let's say the adversary can get hold of the host, can control the operating system and the kernel, and according to the claims of the authors of SGX, the security guarantees would hold. So that raised the bar really high, very high expectations. There was a lot of work on applications of this approach. So I worked in particular on let's say, using this new tool to improve security of software-defined networks. And some examples are, let's say, storing credentials and the crypto libraries that are used by software network components, because otherwise they were stored in plain text. It was not very nice. And then we went further and decomposed a piece of software called Open vSwitch. It's a network component, this virtual switch. And we ported the part that stored the routing tables to SGX enclaves, because I got some feedback from a colleague saying that actually this metadata is very valuable. So it would be good to ensure its integrity and confidentiality, and to protect the ordering of flow rules. So that felt good. But then gradually we started getting more and more feedback from reviewers saying that, well, you're not really addressing the vulnerabilities. And of course, I knew that there were more and more vulnerabilities being published, and perhaps in the first paper, it was quite easy to brush it off and say that, well, they're not yet practical, or not in that adversary model that we consider and so on. But gradually, towards later papers, it became impossible to ignore the reality. And the reality was that there was a tsunami of vulnerabilities being published, and all sorts of vulnerabilities, because since the authors of SGX, let's say, raised the bar and promised or overpromised the security guarantees that the SGX can uphold, the entire, a large part of the security research community jumped into searching for vulnerabilities, and they found a lot. So let's go through some of them. The first type, so this is a kind of an arbitrary categorization of attacks, but let's bear with this. The first type are the control channel attacks. So the main idea that they use is that the adversary has near total control of the operating system and the platform. So that allows them to monitor or introduce page faults, to time interrupts and introduce interrupts while the enclaves are running, and configure and track page table access. So that created, that introduced a whole lot of vulnerabilities that allowed, for example, extraction of cryptographic keys from the enclaves. That was initially brushed off by the vendor, saying that, well, actually side channel attacks are out of the question. We don't consider them in our adversary model. But gradually that became harder and harder to uphold, because another type of attacks were attacks that on the cache hierarchy system. And they relied on this idea that actually caching memory loads from DRAM, from dynamic RAM, left effects on the system state that were measurable outside of the enclave application. So you didn't actually need to be running code inside the enclave. You could be running malicious code on the platform and still observe these states. So it became quite difficult to claim that the adversary model does not include that. And a whole lot of techniques for side channel extraction of data from the cache were used, and there are still many more coming up, and many of them are effective. So the choose of tools might depend on what type of information, the amount of information that needs to be extracted, but there are plenty of ways to do that. And yet another type of attacks that made a big splash in 2016, when they were first kind of introduced and published, they were the speculative execution attacks. And this exploits the fact that modern Intel CPUs, as well as from other vendors, they perhaps execute instructions, many instructions that might later on be discarded, because, for example, the branch prediction was wrong. However, these pre-computations, they still cause measurable changes to the CPU state. And while it was initially thought that they don't affect SGX, very, very soon it was shown that SGX enclaves, the secure enclaves, are also very vulnerable, equally vulnerable to this kind of attacks. So Intel issued a couple of patches that I will talk about later, but they didn't manage to totally fix this, because they cannot, well, it's actually very difficult to address the core or the root core of the problem. It's easier to address the symptoms. And then a different type of say speculative execution attacks, they use the same phenomenon, but they actually use more than that. They use a race condition where unauthorized memory accesses, they remain still available for a short period of time, ephemerally, because the CPU, when it realizes that the instruction that was executed will not be necessary, it issues a rollback, but a bit too late. So this allows to catch this some data and changes in the state. And likewise, it was first claimed that, well, this would only affect usual applications, even though that was already very serious and made a lot of noise in the press. However, it was very quickly shown that it can be extended and used as well against SGX enclave. And then once the vendor Intel thought that they could issue some patches and things will be fine with that, it was let's say a second generation of speculative execution attacks and even more destructive. That's called microarchitectural data sampling, because it relies on sampling data from an undocumented buffer, so-called staging buffer, that is common across all cores, and that also allows to attack enclaves that are located on different cores. Because until then, one common countermeasure, so to say, or recommendation, was to pin the enclave. So the enclave running some secure workload could be pinned to one core, and the rest of the cores could run, let's say, the insecure operating system or whatever other applications. And that was, of course, introducing a bit of a performance hit, but that was still claimed to be a good countermeasure. But then these kind of attacks actually showed that these countermeasures would be useless. They also showed that it is possible to bypass most security boundaries that are used today, widely used today. So JavaScript sandboxes, processes, kernel rings, the isolation between virtual machines, and so on, including SGX enclaves. So this attack works despite the let's say latest patches that Intel issued. And I think that what is most serious about this is not that it's one more type of attack, because we've seen that there are several others equally destructive. But its serious issue about it is that it relies on this undocumented feature that was not documented before in the specification from Intel. And this violates a principle that August Kirchhoff, a Dutch researcher from the 18th century, formulated, saying that the security of a crypto system should rely on the security on the secrecy of the key only, while the design should be open. So still, roughly 150 years after he formulated these principles, Intel decided that it's still better to keep some things undocumented. And it, well, practical reality shows that undocumented features will always be exploited. And the only difference is that in some cases, these exploits are published, and in some other cases, they're not published until someone else discovers them. And then there's one more type of attacks, and that is simply scaling the voltage of the CPU to corrupt enclave computations. So, and that is also that can be done by an adversary who can control the platform and the operating system. And by corrupting the enclave computation, that also allows to extract the data later on. Here we have a partial overview of some of these attacks. We have to really give credit to these guys discovering them. They have good sense of humor and have good imagination for naming them and designing logos for them. Apart from that, this kind of shows the main areas where the attacks are targeting. So it's mostly the memory pipeline, the caches, and here we see this undocumented staging buffer that was also used to let's say, create a whole new type of attacks. What can be done about it? So there's a set of countermeasures, but what is common to all of them is that they don't come for free. So I'm not talking about money, I'm talking about effort, which, okay, you can ultimately translate it to money, of course. So the most effective countermeasure to this would be a microcode patch from the vendor. So that's since CPU instructions are not implemented always on silicon, but most of the complex ones are implemented in microcode. This microcode can be patched, so Intel can even remotely patch microcode on all its CPUs. So this is effective, can work very well. However, it's very costly. So the speculative execution attacks that I mentioned, they were patched with a microcode patch that could be applied. However, if you look in the figures on the right, these are some results that we accidentally discovered while doing other work. This has quite a significant impact. So you see here the different versions of the microcode from 2017 to 2019 that we tried out. And you can see the performance hit that this has. So it takes much longer for transitions in and out of the enclave. And each patch, each update tended to slow it down more and more. So especially this is visible with the warm cache measurements. So as I said, these microcode patches are very effective. They address many of the speculative execution attacks, the data cache loads, the MDS attacks, some of them, not all, and these software fault injection attacks that scale the voltage on the CPU to corrupt the computation in the enclaves. So once again, these are very effective, however, very costly, both in terms of the performance and in terms of issuing them and deploying them on all the running platforms. Then another approach, or a complementary approach, perhaps, is system redesign. So redesigning the entire, let's say, SGX system could help some of the issues, some of the attacks. And examples of redesigning are, for example, changing the supporting enclaves, because SGX relies on several enclaves, such as, for example, the quoting enclave here that you see is used for attestation, for making sure that let's say, a remote party or an end user can verify that the code running in their enclave is authentic, it was not modified, its integrity was not modified. However, this system redesign, it can take a long time, because it also needs to be to go through the entire design process within Intel, and then should be issued and so on. And this most likely will happen with the next platform generation. So we've seen already there was an iteration from SGX1 to SGX2, and this SGX2 introduced a major system redesign to extend functionality, but also improve security based on the published vulnerabilities. But then there's actually a better strategy to push the responsibility to someone else, to the end users, and just say, well, this feature SGX works as it is, and so it's your responsibility to write good code. That's definitely more convenient for you, for the vendor. However, it's been shown time and again that writing secure code is very difficult and takes a lot of effort. And considering the realities of how code is created today, in most cases, developers or their organizations will not want to put in all this time and effort. So hopefully there will be a collection of better solutions, like better compilers or better software development kits to write better software for these enclaves. However, no matter how many such solutions we have, one thing is common to all of them is that they definitely introduce some performance impacts and additional barriers or difficulties in writing and deploying this code. So it doesn't come for free either. Perhaps the performance impact might not be as radical as with a microcode patch that disables hyperthreading, but still they will be notable. And most importantly, in most cases, such measures will help, let's say, raise the bar for the attackers, but will not make the attacks impossible. And then finally, in the same let's say direction, we have another solution, like simply designing the application that is loaded in the enclave, this workload that will be running there. It can be designed better or written better, and so some suggestions, solutions that were proposed is either wrapping the secret data and the secret code that we want to protect into TSX transactions. So these are like extensions for adding hardware support to transactional memory. They help alleviate many of the problems that we talked about, many attacks. Or using oblivious RAM to hide memory access patterns. So oblivious RAM, for those who don't know about it, it's a technique to hide memory access patterns and avoid in this way side channel attacks. However, in my experience, from what I've seen, oblivious RAM has simply gigantic performance hit. So it's very rarely practical. So again, these are very costly mitigations, and they take a lot of time and effort to get right. And even when they're written well, they will have a huge performance impact. And they can fix some of the. Oh yeah, here's an error here. They can fix some issues, but not all of them. But here, to wrap this up, I have this overview that I came up with while preparing these slides. It seems like there's a trade-off between performance on one hand and the choice of a stronger adversary model. So we can have a weaker adversary model and move to the left here and have better performance. But if we want to provide security guarantees in an adversary model where the adversary is capable of more and more changes to the platform, to the operating system, to the components around the enclave, then we have to give up some performance. And not only that, we also have to increase the developer effort, depending on what these measures are. Perhaps microcode patches don't need that much developer effort. In most cases, it would be someone else updating the platform microcode. But all the other measures will require more developer effort. For example, using new APIs, new SDKs, or simply working a whole lot on improving the application design. So this trade-off doesn't seem to go anywhere anytime soon. It seems that we'll have to live with this trade-off between performance and security guarantees. And my conclusion is that it's important to understand all these attacks and the countermeasures, the toolbox of attacks and the toolbox of countermeasures, to know which ones to choose depending on the use case and the application that we're working on. And with that, I will conclude. You have some references at the end of the slides.